So today in this tutorial we will have a discussion on code optimization. So we know code optimization comes after lexical analysis, syntax analysis, semantic analysis, the intermediate code generation, right? After intermediate code generation we go to code optimization phase. So what is the purpose of this code optimization? A code generated by the compiler can be made faster, or it will take a less space, or we can take the advantage of both of them by using this optimization. Okay, so some transformations can be applied to the code called optimization or optimization transformations. And the compiler that is capable of applying optimizing transformations are called optimizing compilers, and it is an optional phase and it must not change the meaning of the program. So 2 points that we have to discuss about the scope of optimization is that it will not change the algorithm. Okay, it will not try to improve the algorithm. Only the code generated by the algorithm will be improved in the optimization phase. And second one is it is not specific to target machine. That is, if we try to exploit the architecture or instruction set of a target machine, we can optimize to the core, but we won't target on this target machine. That is, by fully exploiting its instruction set and so on, we won't do that in this optimization phase. So in the experiments, the compiler was found to consume 40% extra compilation time due to optimization. But the benefit is that program will occupy only 25% less storage and will execute 3 times faster than unoptimized program. Now, what is the need for this optimization phase? One, a code produced by a compiler may not be perfect in terms of execution speed and memory space. So, this optimization will help in increasing the speed and reducing the memory space. Second one is optimization by hand will take more time and also more effort. So, it is very difficult for the programmer to optimize the code. Then another problem is that a programmer will not know machine level details like instructions and addresses. So that level of optimization is also very difficult. So advanced architecture features like instruction pipelining requires optimized code. Then structure reusability and maintainability of the code are improved when we use optimization phase in compiler. So, what are the criteria for performing code optimization? The first is that after optimization, it should not change the meaning of the program, or it should not change the output or produce any error for a given input. So that is called safe approach. Okay. Second one, it should improve the efficiency of the program by reusable amount. Okay. Then third one, it must be worth if with the effort. That is, the effort put on optimization must be worthy when compared with the improvement. We already discussed that optimization will take consume some time, but the better part is it will reduce the execution speed as well as the memory space. So we should ensure that this effort that we put on optimization will become worthy. Now, optimization can be applied in three places. First one is in the source code, second one is in intermediate code, and third one is in target code. So in source code only user can optimize. In the intermediate as well as in target code, it is performed by compiler. And what are the optimization that user perform in source code is a profile program, change algorithm, and transform loops. And in the intermediate code, compiler can improve loops, procedure calls, and address calculations. And in the case of target code, compiler can use registers, select instructions, and do peephole transformations. Now, there are mainly two types of optimization. One is machine dependent and another one is machine independent. So in the case of machine dependent optimization, it will run only in a particular machine. But in the case of machine independent, it can be used for any machine. So this is the organization of code optimization. Now this is a front end and this is a code generation, generator, and this code optimizer will be in between these two and can perform control flow analysis, data flow analysis, and transformation. Now there are mainly two phases of optimization. One is called local optimization and second is called global optimization. So from this statement itself you can guess, right? So transformations that is applied only over a small segment program called base block is called local optimization. Okay, so what is a basic block we will see later. It's a set of statements in three address form, okay, which perform in execution in sequential order, and speed up factor for local optimization is 1.4. Whereas in the case of global optimization, transformations are applied over a large segment of program, like between functions, between procedures, inside loops, etc. A local optimization must be done before applying global optimization. This is very important. We should perform local optimization first. After that only we will be applying the global optimization. And speed up factor in the case of global optimization is about 2.7. Now we discussed basic block, right? So basic block is nothing. It is a sequence of three address codes. Okay, every statement will be written in three address format, and the execution sequence will also be sequential. So basic block is a sequence of consecutive three address statements which may be entered only at the beginning, and when entered statements are executed in sequence without halting or branching. There will not be any halt or there will not be any branches. And in order to identify the basic block, we have to find leader statements. This is important. It's called leader statement. So these are the rules to identify the leader statement. So input is a sequence of three address statements and output is a list of basic blocks with each three address statement in exactly one block. So what are the steps to identify the leader? First is the first statement is always the leader. Okay, the first statement is always the leader. Second is any statement that is the target of a goto is a leader. Okay, any statement that contains the target of a goto is a leader. Then third is any statement that immediately follow goto is also a leader. Okay, and for each leader its basic block consists of that leader and statements up to but not including the next leader or the end of the program. So every block will start with the leader and will stop when it reaches next leader or the end of the program. So we will understand more when we see an example. So a basic block is from a leader statement to all statements up to but not including the next leader. Next is flow graph. Now what is a flow graph? It is the pictorial representation of control flow analysis in a program. Okay, how the control flows in a program. That is, it's the pictorial representation is flow graph, and it also shows the relationship among the basic blocks. Now, it is a directed graph of the form G equal to N, E and N0, where capital N represents the set of basic blocks and capital E represents set of control flows and N0 is the starting node. Now, if there is a direct edge from B1 to B2, it means that the control transfers from last statement of B1 to first statement of B2. So in that case, B1 is called predecessor of B2 and B2 is called successor of B1. Now let us consider an example. So this is an algorithm for performing the quicksort. Okay. Uh, you know how it is performed. We will divide the array into two based on a pivot point, and we will traverse the two different portions, right? And it will be a recursive procedure also. Whenever we will do a comparison, and depending upon the comparison, we will either interchange or we will traverse, right? So this is the code, and from this portion we are discussing. So first step, we will write the intermediate code for this much code. Okay, first step is to write the three address code for this much amount of code. So this is the three address code. Okay, the last tutorial we have discussed how to write the three address code statements. So this is the three address code corresponding to the quicksort program. Now, based on this, we are going to discuss the next topic. So first we will consider how we can draw a flow graph for quicksort from this three address code. So first step, what is the first step? We have to identify the basic blocks. So in order to identify basic blocks, we have to find out the leader. So first statement is always the leader up to either we get into the end of a program or either we get into a go to statement, right? So when we traverse, we will see go to here. So up to this we will consider as a block. So I equal to m minus 1, j equal to n, t1 equal to 4 into n, and v equal to a of t1. So this up to this is a block. Why? Because a label of goto is at 5. So all the statements till label of goto will be considered as a block. So this much is under block B1. Now after that label of goto is the header. So this is my leader. Second leader is I equal to I plus 1 till say go to 5, right? So here 5 is in this I equal to I plus 1. So I am considering it that much portion as block 2. So instead of go to 5, I can write go to B2. Then next leader is j equal to j minus 1 to if t 5 greater than 5 go to 9. I am considering it as block 3. So 9 is replaced by B3. Then this is a statement after go to and it is considered as a leader, right? So since it has a label, it is considered as an independent block. So B4. Then next is leader is T6. Now it will T6 equal to 4 into I. So till go to we will write A of T10 equal to X, right? So this is considered as go to 5. So go to 5 we will consider as B5. Okay, and next block is T11 equal to 4 into I to T15 equal to X. This is considered as B6. Hence we have created 6 blocks depending upon this three-address statement. So leader is always a first line. Then whenever we have a go to statement which shows a label, we will stop there. Then very next statement after go to is the next leader. Thus we will create the blocks. Now this is the control flow. So wherever it says go to particular, we have to draw the line. So here it's go to 5. Go to 5 again this is B2. So again it is going to B2. That is why loop is going to B2 repeatedly. Then after the last statement of B1, it will be going to next statement in B2. That is why there is an arrow from B1 to B2. Similarly, we can draw all the control lines. Now, principal sources of optimization. A transformation of a program is local if it can be performed by looking only at the statements in a basic block. Okay, so when we can perform some modifications in the basic block, it is called local optimization. Otherwise, it is called global optimization. Now, local optimization or transformation can be classified into function preserving transformations and loop optimization. Okay, we are discussing on local transformation, and it can be either function preserving transformations or loop optimization. So under function preserving transformations, we have common subexpression elimination, copy propagation, dead code elimination, constant folding. And under loop optimization, we have code motion, induction variable elimination, and reduction in strength. So in this tutorial, we will discuss each and every one of this in detail. So first one is common subexpression elimination or CSE. Okay, so what is a common subexpression is if we are using a same expression again and again, okay, without its value getting changed, it is called common subexpression. So an occurrence of an expression is called common subexpression if E was previously computed and the value of variables in E have not changed since the previous computation. So we can avoid this recomputation of this expression if we can use a previously computed value. And there are two types within this. One is local and other one is global. So we'll see each of these with an example. See, in this code, T1 equal to 4 into I, T2 equal to A of T1, T3 equal to 4 into J, T4 equal to 4 into I, T5 equal to N, T6 equal to B of T4 plus T5. So when you observe this line of code, you can see that T1 equal to 4 into I and T4 equal to 4 into I. And between these two statements, there is no modification for the value of I. So these two produces the same value. So instead of assigning 4 into I to T4, I can simply omit this T4, right? And wherever I want to use T4, I can directly use T1. That is the common subexpression elimination or within a local block. Okay, so T1 equal to 4 into I, T2 equal to A and T, and T3 equal to 4 into J, T5 equal to N. We omitted this T4, and T6 equal to B of T1 plus T5. So here the common subexpression T4 equal to 4 into I is eliminated as its computation is already in T1 and the value of I is not being changed from definition to use. Now this is another example. See, this is a block 5 that we have created in Quicksort. T6 equal to 4 into I, x equal to A of T6, T7 equal to 4 into I. See, same expression. So we can eliminate this T7. So when we eliminate this T7, here A of T7 become A of T6. Okay. So that is one optimization that is done here. T6 is equal to 4 into I, x equal to ft6. Instead of T7, we skipped it. T8 equal to 4 into j, T9 equal to ft8, and a of T6. Instead of T7, we are using T6. ft6 equal to T9 and a of T8 equal to x. Why? A T10 equal to 4 into j. This 4 into j I have already used here as T8. That is why I am writing f T8 equal to x, omitting this T10. Go to B2. So this is a sub-expression elimination. Okay. Now, even after the sub-expression elimination, there is some problem. See, that is what this is what we did now is a local common sub-expression elimination. Now, how we can optimize it globally is when we check the block B3, we can see that T4 equal to 4 into J. The same thing it is in B5, T8 equal to 4 into J. So we can remove this T8 and can use T4 wherever we find T8, right? So from B3 we will get T4 equal to 4 into J. Thus we can optimize this block as A of T4 equal to X. Similarly, T9 equal to A of T4. That is described here, and this is called global common subexpression elimination. We didn't optimize within a block, we optimize by consulting other blocks also. Now, uh, thus applying this global subexpression elimination, we can transform B5 into this. Okay, see, 1 2 3 4 5 6 7 8 9 codes was here. Now it is only 4 codes. So how it was possible? See, T6 equal to 4 into I, x equal to A of T6, and T7 equal to 4 into I. So T7 is a what repetition, okay, right? So I can eliminate this T7. Similarly, T8 equal to 4 into J, T9 equal to A of T8. Okay, so and A of T7 equal to T9. So if we are eliminating T7, I can omit this statement, right? You can write A of T6 equal to T9. So how we can optimize into this is one, the T2 equal to 4 into I, so B5. So T2 equal to 4 into I, T6 equal to 4 into I. So replace T6 by T2. Okay. So from where we got T2? From here. Okay. T2 equal to 4 into I, T6 equal to 4 into I. Thus by applying this global subexpression elimination, I rewrote, instead of T6, I rewrote here x equal to A of T2. Okay. Then, so x equal to A of T2, that means x equal to T3. Why? T3 equal to A of T2. It is in B2. B2 we have T3 equal to A of T2. So I can write x equal to T3. That is how I got the first statement x equal to T3. Okay. The next is T7 equal to 4 into I. See, same T6, so I can eliminate T7. So I will get T8 equal to T4 and T9 equal to A of T4, right? Now, instead of T7, I am writing T2. So A of T2 equal to T9 and A of T2 equal to T5, right? So I have written A of T2 equal to T5. Now, A of T10 is equal to T4, right? 4 into J. It is in 4 into J, you can see in T4, right? So T4 giving A of T4, instead of T10 I can write T4. So A of T4 equal to X. That is how you got X equal to T3. Then A of T4 equal to X. So hope you have also got A of T2 equal to T5. Okay, why T5 equal to A of T4? That is why instead of A of T4 I have written A of T2. So in turn you will get A of T4. This is the steps. T7 equal to 4 into I. So eliminate T7, I'll get T8. Eliminating T7, I'll get uh, T8 equal to T4 and T9 equal to A of T4 and A of T2 equal to T9, and since we have T5 here, somewhere it is there, T5 equal to A of T4, so I have written A of T2 equal to T5. Okay, so this is how we can optimize B5. So in this same way you can optimize B6 into this. So next is copy propagation. Assignments of the form f equal to g is called copy statements. Okay, so wherever we have g, we can substitute it by f. So it will also reduce the lines of code. So here we have an assignment statement x equal to t3, and here I have a of t4 equal to x. So instead of this x, I can directly write t3. So that is what it is written here. X equal to t3, f t2 equal to t5, f t4 equal to t3, and go to b2. Instead of x, we wrote t3. So this is called copy propagation. And the example is a equal to d plus e here, b equal to d plus e here, and c equal to d plus e. How I am doing the optimization is, I am giving a temporary variable value t equal to d plus e, and I am assigning a equal to t. Now here also I am giving t equal to d plus e and b equal to t. Now instead of this d plus e, I am assigning t to c. See, this is possible only if both the values are same. If both a and b have same t value, we can use this. So an advantage of this is that it often turns a copy statement. It's a advantage. It turns the copy statement into a dead code. So we'll see what is a dead code. So dead code is nothing that if we evaluate an expression and that value is not used further in the program, we will say it is a dead code. So a variable is live at a point in a program if its value can be used subsequently. Otherwise, it is dead at that point. Okay. So here we optimize this, right? Instead of x, we change it into t3. So if x equal to t3, then a of t2 equal to t5, a of t4 equal to t3. Then what is the use of x in this code, right? We are not using x anywhere in the block. So I can simply avoid this x equal to t3. That is what copy propagation always follows a dead code, which can be eliminated. Okay. Another example is I equal to 0. If I equal to 1, a equal to b plus 5. See, initially we are initializing I is equal to 0. Then how can I become 1? Right? So this will not get executed. If statement will not get executed. So it is a dead code. So next is constant folding. So constant folding means if in the compilation time itself we can calculate a arithmetic value, then it can be substituted in all other statements in which computation is required. It is called constant folding. For example, if we have a equal to 3.14157 by 2 and this a is again used in somewhere, we can replace this a value by 1.57 so that we can eliminate this division operation. Okay. Next is loop optimization. So, a runtime of a program can be improved if the number of instruction in an inner loop is decreased. Okay, even if there is an increase in the amount of code outside the loop, if we can decrease the number of codes in inner loop, the running time of a program can be improved. And mainly three techniques are used: code motion, induction variable, and reduction in strength. So we will see each of them in detail. First is code motion. Okay, it's an important modification which can reduce the amount of code in a loop. So execution time of a program can be reduced by moving code from a part of program which is executed very frequently to another part of program which is executed fewer times. Hmm? So example is a loop invariant code motion. So what is a loop invariant? A fragment of code that resides in the loop and computes the same value of each iteration is called loop invariant code. Okay, that code will lie within the loop, and each time the code is executed it produces the same value. It is called loop invariant. For example, consider the particular code. For I equal to 1 to 100 begin, a z equal to 1, x equal to 25 into a, y equal to y, x plus z, and end. See, every time the loop is executed, x into 25 into a is constant. Every time we are performing a multiplication operation there. So how we can optimize? We can move this loop invariant outside the loop. So x equal to 25 into a, we moved it outside, and remainder we have kept it in the loop. So this is the example for code motion. Next is induction variable. Um, Consider the loop, the values of j and t4 remain in lockstep. So what is that? Lockstep means whenever j is decremented, we are performing 4 into j. So after decrementing, we are performing 4 into j, which in turn decrements the value of t4 by 4. For example, if j is equal to 5 initially, j equal to j minus 1, we will get 4. Then t4 value will be 4 into 4 equal to 16. At the next iteration, j equal to 3. Okay, and j equal to 3, t4 equal to 4 into 3 equal to 12. So we have subtracted t4 by 4. So that is the operation. So it is in lockstep, means whenever this is executed, this will also get executed. So every time the value of j decreases by 1, that of t4 decreases by 4. Such identifiers are called induction variables. The next is reduction in strength. Reduction in strength means we can reduce the power needed for execution. We know that multiplication will take more CPU time, okay, compared to addition or subtraction. So if we can move that multiplication, we can change that multiplication to subtraction or addition, it will reduce the strength. So that is the what we are doing here. So in the same loop, j equal to j minus 1, t4 equal to 4 into j, what I am going to do is, instead of 4 into j, I am replacing it by t4 equal to t4 minus 4. And initially t4 should get some value, right? For that, I am taking this initialization statement, this t4 equal to 4 into j, outside the loop. Okay, that is why I have included this statement in v1. So I equal to m minus 1, j equal to n, t1 equal to 4 into a, and v equal to a of ti. t4 equal to 4 into j. I'm taking it into v1, and here I have modified this multiplication into subtraction. Okay. Now optimization of basic blocks. Many of the structure preserving transformations can be implemented by constructing a DAG. Okay, so there is a node n which is associated with each statement within the block. For each statement within a block, we will create a node, and children of these nodes corresponding to statement that are last definition prior to s of the operands used by s. We'll understand this one seeing an example. So direct acyclic graph is an abstract syntax tree with a unique node for each value, and it is a useful data structure for implementing the transformation on basic block, and it is usually constructed from 3 address code. Now this is an expression, okay, a equal to b plus c, b equal to a minus d, c equal to b plus c, and d equal to a minus d. So how I can construct a DAG is, first is a equal to b plus c. So a, this is our node, equal to b plus c. Then b equal to a minus d. I have minus operation here. So b equal to a minus d. Then c equal to b plus c. So here I have c equal to b plus c. Again I have d equal to a minus d. So I have already a minus d here. So for b, so I'll just put a comma d, because b and d are having same operation. So this will help to identify whether there are common sub-expressions. Now application: determine common sub-expression, determine which names are used in block and compute outside the block, determine which statement of block could have their computer value outside the block, and simplify the list of quadruples by eliminating common sub-expression. Rules are: a leaf node will represent identifiers, names, and constants, and interior node always represents operators. And second one is, while constructing the DAG, there is a check made to find if there is an existing node with same children. So a new node is created only when such a node does not exist. Okay, we have seen the previous example. As there was b already, we just kept it as comma d. An assignment of the form x equal to y must not be performed until it is a must. So here a equal to b plus c, b equal to b minus d, c equal to c plus d, and e equal to b plus c. See, e again b plus c. I didn't give uh, what as the equal to symbol. Similarly, d equal to b plus c, and e equal to a plus b, and again b equal to b into c. Here I have given comma b, and a equal to e minus d. Here I didn't give b plus c again and again. Why? Because there is a modification value of b and c, right? So a and e are different values, but here there are b into c and b into c. Here both are same values because there is no modification to value of b or c. And we can use this algebraic identities for optimization. That is, if there is x plus 0 or 0 plus x, we can directly write x minus 0 as x into 1 or 1 into x as x by 1 as x. Another class is reduction in strength, that is multiplication to addition or subtraction. The exponent of 2 I am writing as x into x. 2 power x I am writing as x plus, sorry, 2 into x is x plus x. X by 2 I am writing x into zero point 0.5. Similarly, we can make use of this assignment statements, sorry, associative laws. And with the intermediate code, a equal to b plus c, t equal to c plus d equal to t plus b. Okay, what I have rewritten this into intermediate code. And if I am taking this outside the block, I have written like this. If I am not taking this outside the particular block, I can simply write a equal to b plus c and e equal to a plus d. Okay, no need of this temporary variable t if I am not using the sequence outside the particular block. So hope you have understood this tutorial. For watching.